Before we begin, I just wanted to give the notation here. 6.3.01. So the 6.3 means chapter 6, section 3. So it's section 6.3. And zero point zero 0.01 just means the first video that I'm making on this section. This is Miramar College Math 122, otherwise known as Business Calc 2. When you have a simple integral like this, a very straightforward integral, so the integral of e to the x dx, that's just e to the x, and of course plus a constant. Later we learned a little more complicated case, and that's the integral of 2x e to the x squared dx, and that we're able to solve that as e to the x squared plus c. How did we solve that? We used u substitution. Can you remember how to do the u substitution here? I want you to pause the video, see if you could solve this with u substitution. And the way to solve it with u substitution is to let u equal x squared, so du equals 2x dx, and that's going to just solve everything hunky-dory. But now I want to look at another kind of integral, the integral of x e to the x dx. It's not straightforward like this top guy here, nor can I use u substitution over here, because if I will, for example, if I would let u equal x up there, du would equal dx, but I would never account for this x out here. I'd be stuck. U substitution ain't going to work. So I'm going to have to do something drastic. I'm going to have to develop a whole new technique. But once I develop that new technique, it's going to make a lot of integrals a lot easier to solve. So I'm going to start with something we know from calculus, the product rule. The derivative of a product, uv, u and v are both functions of x. The derivative of the product uv is equal to uv prime plus vu prime, or I'm just writing it this way, u dv dx plus v du dx, that we know from the product rule. And now I'm just going to integrate both sides. When I integrate both sides, what's going to happen is that the integral and the derivative are going to kind of basically cancel out. I'm just going to be left with the plain uv. Here I just have the integral of u dv, and here I have the integral of v du. Now I'm just going to solve for the integral of u dv right here, and I get this famous classic formula. And now I have integration by parts. This formula gives us a technique of integration by parts. By the way, I put those little integration signs here. The integral of the derivative is just the original function. This is just integral of u dv, and that's the integral of v du. Now, I know what you're all thinking. What did I accomplish? It looks like I accomplished absolutely nothing, because I took some mumbo jumbo and now I have just some more mumbo jumbo. So how is this going to help us in any way solve any integrals? And in particular, how is this going to help us solve the integral we started with? I left you on this big cliffhanger. How are we going to solve that problem? So let's go back to that problem. Here's the problem we wish to solve, the integral of x e to the x dx. So we're going to use this technique of integration by parts, and here's what we're going to do. The first thing you have to do is you have to look at the integral and decide, so to designate what should be u and what should be dv. Because we're going to look at this integral as though it's the integral of u dv. So here's how we're going to do in this case. I'm going to designate the x as my u and the e to the x dx as my dv. So this now is the integral of u dv. And now before we go and use the integration by parts formula, we have to establish a few things. And we're going to need u and du and v and all that stuff. So if we know u is x, that's what we decided. We know dv is e to the x dx because that's what we decided. That's the decision we made. Now, if that's u, du is equal to dx, there's differentiating. And if dv equals e to the x dx, then v is just e to the x. And that I got by integrating. So if I went from dv to v by integrating. I went from u to du by differentiating. I established the u by choice and I differentiated. I established the dv by choice and integrated it. I made this choice because I actually tried other ways and they didn't work out. And you could do that with trial and error, but this worked beautifully. So next. Now I can say that the integral of u dv is equal to uv minus the integral of v du. Again, that's my u, that's my v. How do I know that's v? Because I figured it out over here. The integral, that's v, because I figured it out over here. And this is du, because I figured out over here what du is. By the way, notice I just want to point out that when I don't write here e to the x plus c. We're going to save the c for the end. In other words, that's dv is equal to e to the x dx. I integrated to get v, but I'm not putting a plus c at this point. We're going to stick the plus c on way at the end. Anyway, what did I accomplish? I wanted to solve this integral here, but all I got was an expression with another integral. See, when you solve an integral, the idea is to have no integrals here, just have plain functions. So what did I accomplish? Well, I'll tell you what I accomplished. Yes, I started an integral, I ended up with another integral, but the other integral that I ended up with is much, much easier to integrate than the original guy was, because this here is just our straightforward case. So I'm going to just give our final answer. X e to the x minus e to the x plus c. So the integral of x e to the x dx is equal to x e to the x minus e to the x plus c. Where did that minus e to the x come from? Because the integral of e to the x is just a straightforward e to the x. So it's minus e to the x. Pow. That is the answer. Yay.